Welcome back to Differential Calculus. In this video, I want to talk about two more rules for differentiation, the product rule and the quotient rule. Let me get my head out of the way, and we will start with the product rule, which, as the name suggests, allows us to differentiate the product of two functions that I'll name as u of x and v of x. Product rule tells us we're going to have u prime of x times v of x plus u of x times v prime of x. No one can seem to agree on what order those two things should show up in. Conveniently, they are being added together, so if we switch the order, it doesn't make any difference whatsoever. As I've done a couple of times, I'm going to go through and try to show you a little bit of where this came from. And as I've said in previous videos, please listen to what I'm talking about. Try to get the sense of the overview of what's happening, but don't worry too much about all of the, don't worry too much about all of the minute details. The crunchy algebra is not the point. It is a distraction, and I've thought about whether or not I should include these, but I think that seeing that it does come from something is very valuable, so I think it's worth it even if the algebra does get messy at times. And I'm going to use the x goes to c limit definition of the derivative in this case. And immediately I am going to use mathematicians' favorite trick of adding and subtracting something that wasn't there before. In this case, u of c, v of x. Doing that will allow me to split this limit up into two. And then I can look at each on their own. In the first limit, there's a in the first limit, there's a v of x in common. In the second limit, there's a u of c in common. I can factor those things out. A little bit weird in that first one. My v of x turns into a v of c because I am taking the limit as x goes to c. But then I'm left with this limit here, which is just the definition of u prime of c. And I'm left with the limit here, which is the definition of v prime of c. So I get the expression that I was expecting to get. With the functions that we know how to differentiate so far, the product rule doesn't get us all that far. But we can do something like, if I want to take the derivative of, let's say, x squared times the square root of x minus 1. Algebraically, I could bring that x squared inside the square root. I could do some manipulations and use the chain rule in order to differentiate this. That might be easier than what I'm about to show you, but I wanted to use this specifically as a chance to highlight the product rule. So I've got that u of x is x squared and v of x is the square root of x minus 1. If we take a couple of minutes and work through those derivatives, u prime of x is 2x and v prime of x is going to be 1 over 2 square root of x minus 1. All right, if you're not confident on those, take a couple of minutes using the product rule and actually even using the chain rule. Right? Square root of x minus 1, I'm going to rewrite as x minus 1 to the 1/2 power. So it's 1/2 times x minus 1 to the negative 1/2 times the derivative of x minus 1, which happens to just be 1. All right, so I know I'm going through things quickly there. If you want to take the time, slow down, and work through those on your own, I encourage that. But I'm looking at the big picture here. This is the derivative of u times v, which my product rule tells me should come out as u prime times v plus u times v prime. In this case, u prime is 2x, v is the square root of x minus 1, u is x squared, v is 1 over 2 square root of x minus 1. And if I was the one doing this on an exam, I would probably leave the result there. That is perfectly fine as far as I'm concerned. But if you're checking an answer in the back of a textbook, you'll see a little bit more work done from here. I can find some common denominators. All right, if I take that first one and multiply top and bottom, all right, well, let's make sure that there is a bottom. Multiply top and bottom by 2 times the square root of x minus 1, and I will get 2x times x minus 1 over 2 square root of x minus 1. And then I have x squared over 2 square root of x minus 1. I can distribute in the numerator 2x squared minus 2x, and then plus x squared from the second fraction, all over 2 times the square root of x minus 1. And combining some like terms gives me 3x squared minus 2x, all over 2 times the square root of x minus 1. Did that do anything useful? I have no idea. Again, in the context list, here's a function, take its derivative. I don't have any way of judging whether this is better or worse. In some contexts, taking the time to clean up the algebra like this is useful. In some contexts, a little bit less so, and leaving your solution like that would be perfectly fine. But you should at least be familiar with the fact that this is something that can be done, so that if you're checking an answer in the back of the book, you can look and say, oh yeah, that's the same thing I have, you just have to do 5 steps of algebra. Which, no, I don't expect you can do that offhand, but you look at something like that and say, wait, that's not what I have, but I can try to do algebra to get there. Try to work through the algebra, see if you get to the same place. If you do, chances are that you're in good shape. All right, so there's the product rule. Let's now look at the quotient rule, which, as the name suggests, is what you do when you take the derivative of division. U of x over v of x. And the quotient rule is very messy at first glance, but after you get a little bit of practice working with it, it will be relatively easy to work with. The derivative of u of x over v of x is u prime of x times v of x minus u of x times v prime of x all over v of x squared. And trying to remember this, a couple of things to notice here. Well, those are the same two things that we added together using the product rule. It's just that now instead of adding, they're subtracted. And then we take our denominator and we square it, which is a little bit weird, but we can figure that out. Once again, I want to kind of show you where this comes from, and I really like doing this one, and this is one that you should be able to follow along with, because I am not going to have to go back to the limit definition. We have finally gotten far enough that I can do this using the rules of differentiation we've already established. Specifically, I'm going to do that by rewriting this as u of x times v of x to the negative first power. So, using the product rule, I'm going to have u prime of x times v of x to the negative first power plus u of x times the derivative of v of x to the negative first power. And I have to write it out like that because it's not v prime of x. I have to use the chain rule there. But just for the sake of cleaning up my writing a little bit, let's go ahead and rewrite this as u prime of x over v of x. right? That's the same thing as u prime of x times v of x to the negative first. And then we'll have u of x times the derivative of u of x to the negative first. All right, so using the power rule, this is going to be -1 times v to the -1 minus 1, which is -2. And I'm suppressing the of x here again just to make the writing a little bit more readable. But then I have to multiply that by the derivative of v of x, which is v prime of x. All right, let's clean this up a little bit. U prime of x over v of x plus u of x v prime of x, and there's a negative in there, so instead of plus, I guess this should be minus, and then I have v to the negative second, v of x, the whole thing squared, in the denominator. One last step. Let's find common denominators by multiplying that first fraction top and bottom by v of x. And then combine everything together because I now have two fractions being subtracted that have a common denominator. And that gets us the quotient rule that I said we were going to get at the start of this little bit. The quotient rule for right now is definitely more powerful than the product rule because we don't have that much that we can multiply together. But dividing some polynomials is something that happens all the time. And so we might end up in a situation where we want something like the derivative of x squared minus 5 over 5 minus x. Right? That is a fairly natural, rational function. It's a little bit messy. It looks like we should be able to clean something up somewhere, but unfortunately it doesn't actually work. And we're left with no choice but to just dive in and see what happens. We'll go ahead and let u of x be the numerator, x squared minus 5. We'll let v of x be the denominator, 5 minus x. We will differentiate. U prime of x is going to be 2x. We'll differentiate over here. V prime of x is going to be -1. And then from there, it's just a matter of following the formula. I can even scroll up a little bit so the formula is still on the screen. All right, I'm going to have u prime, which is 2x, times v, which is 5 minus x, minus u, which is x squared minus 5, times v prime, which is -1, all over v, which is 5 minus x squared. Then doing a little bit of algebra to clean up here. That page break falls on a very annoying part of my screen right now, but that's okay. Let's see, I'm going to end up with 10x minus 2x squared minus a minus is plus x squared and minus 5 all over. I will leave that as 5 minus x squared. I probably won't be able to factor anything, but just in case, I'll go ahead and leave that like that and see what happens. Clean up, combine some like terms. I'm going to end up with minus x squared plus 10x minus 5 all over 5 minus x, the whole thing squared. There's no such thing as two numbers that multiply to 10 and add to 5, so that numerator does not factor, and in fact, that is all the further we can take it. All right. So a couple of takeaways on this video. The product rule, the quotient rule both allow us to deal with things that we might not be able to otherwise. Also of very important note in this video is that when you're taking the derivative of a fraction, things get a lot messier, which is opposite of what you might have started to get the expectation of based on when we were taking derivatives of polynomials, where the derivative of a polynomial is always a simpler function. The derivative of a rational is almost always a much, much, much more complicated function. All right. We'll wrap up, as always, with one for you to try on your own. How about the derivative of x over the square root of x minus 1? All right, this is not as simple as it looks, and it doesn't look all that simple, but take your time, be careful step by step with your algebra, and I think it'll be okay. See what you can do with that, and I'll see you in the next video.